This is Electric Circuits course of second semester offered in 2020 in the Department of Electrical Engineering. This is the textbook we are using, and I am Dr. Khalid M. Hassan. In this lecture, we'll discuss chapter 6, which is on capacitance and inductance. In part 1, we'll discuss three things: capacitor, inductor, and IV characteristics of capacitor and inductor along with the waveforms. And at the end of this part 1, we'll discuss equivalent capacitance and inductance. In part 2, we'll discuss dynamic operational amplifier circuits. Means operational amplifier circuits which uses capacitors and inductors. You know from physics course at college level, the basic form of a capacitor, if we have two metal plates and in between a dielectric, it forms a capacitor. Further details are given in section 1 of chapter 6, and all students are advised to go through it by yourself, as it is also part of college physics. Symbol of a capacitor and the direction of the current, we show it like this, like we have been doing it in case of resistors, and we also show the polarity. There are various forms of capacitors: ceramic capacitor, film capacitor, electrolytic capacitor, high voltage capacitor, air tunable capacitor. Air tunable capacitor means we have parallel plates, and in between parallel plates the dielectric material in here is air, and if we move the knob over here, the capacitance will change. And the last type of capacitors shown in this slide are trim capacitors. Basically, we have parallel plates of D-shaped parallel plates, and in between parallel plates dielectric. There is a dielectric material. It's a plastic paper type material, and we can adjust the capacitance with the help of a screwdriver. In the capacitor, the current and voltage relationship, I will start from the current relationship of the textbook of the capacitor, and before all the properties of capacitors discussed before this are self-study. So in a capacitor, the current is equal to C times the time rate of change of the voltage across the capacitor. The voltage across the capacitor with this polarity and with this direction of the current. This is very important. All these relations, they use this passive sign convention. With this voltage polarity and with this direction of the current, the mathematical expression of the current IC is C dVc by dt. Now, if we manipulate it mathematically, if we take integral of both sides, and then we reach this, and further if we operate this integration from t0 to some time and t0 to t, we end up over here, and then finally the final relationship of the capacitor is Vc naught plus 1 over C integral from 0 to t ICx dx. In here, this Vc0 means the initial voltage across the capacitor. If the initial voltage across the capacitor is 0, if the initial voltage across the capacitor means the voltage across the capacitor at time t equal to 0. If it is 0, then this will disappear and we'll have only this expression. Next is the power and energy relationship. As you know, power is product of voltage and current, and especially in DC circuits, the power is the product of voltage and current, but this is shown power with the T parameter. This is instantaneous power, power at any time instant. This is the product of voltage and current. When PCT means the power related to the capacitor. We know what is IC and VC. IC, as we have seen in the previous slide, IC is C dVc by dt, and we just rearrange these terms. We write VC first, and IC is C dVc by dt. This is equal to derivative of 1 by 2 CV square. As we also know that power is time rate of change of the energy, and energy is integral of power. Energy is integral of power. If we uh, integrate both sides of this expression, we have this from one energy level to another energy level. This energy level relates to time t1, and this energy level relates to time t2. And finally, we have Wc, energy stored in a capacitor, is half Cv square. Energy stored in is half Cv square if we take integral. This is what is energy? Total energy stored in a capacitor is integral from T1 to T2 of Pt. What is P? P is the whole expression. P is the whole. So if we integrate this, the integration and d by dt will be cancelled, and we will have 1 by 2 Cv square plus a constant. And this constant, due to the integration, is related to the energy stored in the capacitor. When the initial energy stored in a capacitor is 0, we have simply 1 by 2 Cv, 1 by 2 V square, the voltage across C. We also call it quickly half Cv square. The capacitor is a dynamic circuit element with the following properties. Dynamic circuit element means its voltage current properties are related to time. The current through the capacitor is 0 unless the voltage is changing. As you have seen in the previous slide, IC is C dVc by dt. So if there is no change in the voltage, then dVc by dt, which indicates the change, will be 0 and the current will be 0. If the current is 0, the capacitor acts like an open circuit to any DC excitation. The voltage across the capacitor is a continuous function of time. The voltage is 1 by voltage across the capacitor is, as you have seen in the previous slide, 1 by C integral of I dt. So integral of I dt. Therefore, the voltage across the capacitor is continuous function of time. A discontinuous change in capacitor voltage would require infinite current and power, which is physically impossible. So the voltage will change if some current is flowing through the capacitor, and in order to change the voltage suddenly from one level to another level, we need huge current which should flow through the capacitor, which is not physically possible. A capacitor absorbs power from circuit when storing energy and returns previously stored energy when delivering power. The net energy transfer is non-negative, indicating that capacitor is a passive element. Now, we know the capacitor's current C dVc by dt. As long as there is the voltage across the capacitor is changing, current will be flowing. But when there is no change in the capacitor, there will be no current. So if this is the waveform of the voltage across a capacitor, we can find the current. What is current? C dVc by dt. So what is the rate of change from here to here? From t0 to 2 millisecond, from 0 to 2 millisecond, this is the current flowing through the capacitor, voltage across the capacitor. And what is dV of this voltage? What is d by dt of this voltage? Initial value, final value minus initial value, 10 minus 0 divided by this time minus this time. So 10 minus 0 is 10, divided by 2 minus 0, 2 millisecond. Therefore, and the C, if we multiply it by the value of the capacitor, which is not shown here, I missed that. You see the textbook. Knowing the capacitance, then we can find the voltage. And from here to here, for the next time segment, from 2 to 2 millisecond, from next time segment, what is the function of the voltage? It is 3 minus 10, minus 7 divided by 1 millisecond. This is dV by dt. You know, dV by dt is negative in this case, as the capacitance is positive. It is always positive, and dVc by dt during this time segment is negative. Therefore, the voltage will be negative. I haven't mentioned the capacitance in farads. See the textbook for the capacitance in this example, and you will see that the voltage is minus 2.5 volt. Again, few words about this these voltage current waveforms. dV by dt is positive, the voltage across the capacitor is positive. dV by dt is negative, the voltage across the capacitor is negative. Now from a time equal to 3 millisecond and onward, there is no change in the voltage, and rate of change of the voltage is 0. dVc by dt is 0. Therefore, the voltage, the current flowing through the capacitance is 0. And we have seen in the previous slide that the current is flowing as long as voltage is changing. Voltage is changing, and this change is positive. There is voltage, the current is positive. Positive means, see the second slide using passive sign convention, and rate of change is negative, it is negative. There is no change, there is no current. Again, the capacitor, if this is the waveform of the current flowing through the capacitor, this is the waveform of the current, and we have discussed this composite waveform in chapter number 5, and the mathematical expression of this composite waveform is shown over here. It is I naught and exponential function multiplied by ut. This ut is to emphasize that the current, this is 0 from minus infinity, from t minus infinity to 0, it is 0, and the current starts from t equal to 0. Again, we use the t by tc instead of t on the horizontal axis. This is a common practice. You can use t, and if you use only t, then you will write here tc, 2tc, 3tc, and so on and so forth. We know what is the voltage across the capacitor. This is 1 by c times integral from 0 to t of the current plus in any initial voltage across the capacitor. If initial voltage across the capacitor is 0, then we integrate the current, and if we integrate this current over here, then this will be the voltage. You are assumed to understand how to integrate this, and how we achieve this. Do it by yourself and then plot it. For t equal to 0, this will be 0. This will be 1 e raised to the power minus 0 or plus 0 is 1. 1 minus 1 is 0. So this is the voltage across the capacitor. For t approaching infinity, this thing will disappear, and we'll have only 1 over here. and as t approaches infinity, the final value, we also call it final value, the final value of the voltage across the capacitor is I naught Tc divided by C. Again, this is the voltage across the capacitor and this is the current, and related to this voltage and then the current, we can compute the power, instantaneous power over here, power at all instants of time. So take this value of voltage and this value of the current and show it over here. As it is linearly increasing and this is constant, you can take this value, this is 10, and this value at this 2 millisecond is 2.5, therefore it is 25. As current is in milliampere, this will be milliwatt over here straight, and then take this value of the current and for this segment and for this segment and so on and so forth. You can find the power. What is energy? Energy is time integral of power. Time integral of power. I will advise you to find the mathematical expression of this as y is equal to mx plus c, equation of a straight line. So here our y is p and x is t. So PCT is m t plus c. So mt plus c, find the expression, you will have an expression like at. I'm saying at of this. A determines the slope, and if you integrate at, it will become at square. A square term in time will appear, t square, and this is the sketch of t square term. Then after that, find the expression of this and you will find this. And finally, this is finally it is 0, and in the integration, the level over here, level of energy which the capacitor has achieved over here will remain same, because after that there is no current flowing through it and the voltage remains same. Voltage is constant and there is no current. There is some energy stored in the capacitor. Now the inductor. Again, I will say, if you don't mind, the basic principle of the magnetic flux surrounding a current carrying coil due to your college physics. And this is the symbol of an inductor. Always remember the sign, the polarity of the voltage and direction of the current. We will be using this passive sign convention for the relationship of the current and voltage, voltage across the capacitor and current through the capacitor with this polarity of the voltage and direction of the current. Here are various forms of inductors. Toroidal, axial, apparently it looks like a resistor, but these are inductors. And this is choke type inductor, and this is air coil. In this choke type, there is a core in it, not visible clearly, but there is a core over here. And this is a surface mount inductor of very small values. So these are the surface mount inductors. Surface mount, you can see over here of this side. So this is a terminal and other terminal is on the other side. It can be soldered on the surface of the printed circuit board. Likewise this and this as well. And this is a simple air coil inductor, and this is bobbin wound inductor. It is just like a step down transformer shape. You may have seen it before. In the inductor, I will start from the voltage relationship. VL is equal to L dIL by dt. Inductor and capacitors are dual of each other in voltage and current relationship. Dual means the behavior of voltage in capacitor is similar to behavior of current in the inductor, and behavior of the current in capacitor is similar to behavior of the voltage in the capacitor. If you remember, in the previous slide, we have said that IC is equal to C d VC over dt. So instead of I, this is VL L di L t by dt, and I hope you will follow the textbook in order to reach this point. I'm starting from this due to limitations of time. VL is L di by dt. Then the following steps are simple mathematics. It is integrate both sides. We'll have this, integrate both sides, operate this integration. So this is integral of DIL is IL T naught to IL T, DIL 1 over L 0 T naught to T, VL X dx. This is a dummy variable. This is a mathematical necessity dx and VLX. And further, if we have integral sign and d operator over here, it is simply ILT minus ILT naught, and you know we'll reproduce it as such, because we don't know what is VL. Until and unless we know the expression of VL, we will leave it as such. And this factor, if we show it to the right hand side, it will be IL0. So this will be known as initial stored energy at time t equal to 0. And this is the expression of IL. This is not clearly visible. This is IL is IL initial stored energy in the inductor plus I1 over L integral of the VL. Recall that in case of a capacitor, this is VC is VC at time t equal to 0, 1 over C and integral of IC x dx. One thing which is important is that you may be using state variables, especially in the following semester's courses. State variable related to capacitor is the capacitor voltage, and state variable related to inductor is the inductor current. Now, power and energy relationship of the inductor. So I hope you must be able to go through it, as it is just like the power and energy relationship of the capacitor we have discussed in the previous slide. So follow these steps, you will reach this. And this is the energy stored in an inductor, half Li square. I is which is the current flowing through the inductor. If there is some energy already stored in the inductor, then it will be shown over here. The inductor is a dynamic circuit element with the following basic properties, and we have discussed the properties of capacitor, and these are similar properties of the inductor. As the inductor voltage VL is L di by dt, so as long as di by dt is 0, it means there is no change in the current, which means there is some fixed amount of current flowing through it, or in other words, a DC current is flowing through it. Whatever is the value of the current flowing through the inductor, if it is constant, it means di by dt is 0, therefore the voltage will be 0. It is not possible to change the current suddenly or discontinuous change in the inductor current is not possible, because in case of discontinuous change in the current due to sudden change of current, we will require infinite voltage and power, which is not possible. Like capacitor, the inductor absorbs power from the circuit when storing energy and delivers power to the circuit when returning previously stored energy. Now, for a given current, we will see the voltage across the capacitor. So the current through a 2 millihenry inductor is as shown, 4 sine 1000 t plus 1 sine 3000 t. Note that in chapter 5 we discussed sinusoids of the same frequency. Here frequency is different. So basically the amplitude of this low frequency component is 4 and the amplitude of 3 times this frequency is 1. So there'll be basically we have this is 4 as the cursor is moving. This is 4 sine omega d, and in it we are adding 1 sine 3000 t, and this is the resulting waveform. You can use MATLAB or any other waveform in order to plot the waveform of IL. What is the voltage across the capacitor? We know VL is L dIL by dt, and I hope you should be able to uh, do the integration with this. It is L times, it is 2 millihenry and d by dt of this, and you all know this. And if you plot the resulting voltage, this will be the form of the voltage. Now, we see, if you see over here at the peak, so exactly at the peak there is no, the current is constant, there is no change in the current, exactly in the vicinity of this peak di by dt is 0, therefore the voltage is 0. This is the negative peak over here, or over at this surface, at this point, exactly in the vicinity of this point, the rate of change is 0, there of the current is 0, therefore the voltage is 0, and similarly in all other cases. So here the rate of change is maximum, the rate of change in the current is maximum, and it is negative, therefore we have a maximum negative voltage over here. So I advise you to find L di by dt from this I, and due to this 2 millihenry, and plot this to have this to verify it. Be careful about the units of time and units of the current. Millisecond, it may be micro, nanosecond, and this may be ampere, milliampere, microampere. Units are very, very important. Now again, a 2.5 milli, in this example, a 2.5 millihenry inductor is a damped sign. The current through, this is the current through to millihenry inductor, and this is a composite waveform. We have discussed it in chapter 5. This is a damped sinusoid, and this is a damped sinusoid. It is 10e. This is e raised to the power minus 500t raised to the power. Be careful about that. There is a mistake in it. I will just correct it. This is read this as e raised to the power minus 500. It is difficult to write with the cursor, with the mouse over here. This is like this. Be careful about this. So this is a mistake in it. There is a mistake in it. So rest is simply mathematics, and a rather simple mathematics. What is voltage? L di by dt. I is given, so find L di by dt and plot it. What is PL? It is instantaneous power, IL and VL. So multiply this voltage with this current, you will have this, and multiply each time instant on the similar time instant, find the product, or do it mathematically. Multiply I and V, mathematical expression of I and V, and simplify it. You must have this, and this is the energy stored in the capacitor. It is half Li square, as this is the current, and I square. Current is positive, As long as current is positive, inductor is storing energy, and current is negative, inductor is delivering energy back to the system, and then again storing energy, delivering energy, storing until it becomes zero. So as long as it is storing and it's positive, so I square square of a positive term is positive and it is reproduced over here, but the square of this negative term from here to here is also positive. Therefore, the current, irrespective of the polarity of the current, I square will always be positive. Therefore, this is the energy level. So energy level is increasing, decreasing, increasing, decreasing, and so on and so forth. Equivalent capacitance. In the equivalent capacitance, I will go through it very quickly because you know it due to college physics. This is the rest of the circuit, and the voltage over here is Vt, and capacitors are connected in parallel. The current flowing to this parallel combination is I, which is equal to I1, I2, I3, I4 to In for n capacitors. Because these capacitors are connected in parallel, therefore voltages are same. V1, V2, V3, Vn, they are same. Now this is the equivalent capacitance. If we have equivalent capacitance over here, the same current must be flowing. This current and this voltage must be same. The voltage and current must be same if we find the equivalent capacitance, which is shown over here. What is V1? What is I? I is equal to I1, which is C1 dV by dt, I2 C2 dV by dt. So it is always dV by dt as the voltage is same, and dV by dt is a common term. We take it common, and inside the bracket we have C1. And for this, what is the current flowing through it? It is C dV by dt. So comparing these two, we have equivalent capacitance is C1 plus C2 plus dot 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 Cn. Note that if the capacitors are connected in parallel, their capacitance will be added. This is opposite to resistors. Resistors are added when they are connected in series. This is the difference. This is the big difference, a significant difference in the behavior of capacitor and the resistors. When capacitors are connected in parallel, the equivalent capacitance will be sum of all the capacitances. When capacitors are connected in series, we see that if the capacitors are connected in series, the current flowing through all the capacitors will be same. Current flowing through, however, the voltages will be different. Voltages will be different. Voltage will be depending on the value of C1 and C2 and so on. So I1 is equal to current I2, I3, I4, all the currents are same. And what is the voltage? What is this voltage? This voltage is sum of all the voltages. This voltage is V1 plus V2 plus and so on and so forth. So this is the voltage, and we know the voltage sum of all the voltages, and this is the common term. You know, this is the common term. This is the common term in all these. This is common term. Take it outside the bracket over here. This is, and see what is inside, and we have 1 over C1, 1 over C2, 1 over Cn, and this is the initially stored energy. And if the initially stored energy is 0, then the the equivalent capacitance is 1 over Cn, 1 over C equivalent, 1 over C equivalent is equal to 1 over C plus 1 over C2, and like that. Equivalent inductances, if inductances are connected in series, they are added like a resistor. If the inductances are connected in parallel, the parallel inductance will be according to the resistors. This is due to the voltage and current relationship of inductance. Now here is an example with the capacitors and inductors, and we will find a circuit with only one capacitance and one inductance. So you know these two inductors are in parallel. Find parallel combination of inductors. These two are in parallel. This is the parallel combination of inductors. These two capacitors are parallel. Find the parallel combination, equivalent of this parallel resistance, and this will be 5 picofarad plus 1 microfarad. So add these two, it will be this. 0.05, this is 0.05, 0.1, this is 0.1, 1 milli, 1 milli, and I will be showing it stepwise. So in this step, we have combined these two by finding parallel equivalent inductance of this parallel combination over here and combining these two to find the equivalent of this parallel combination over here. Now next, find the equivalent of this series combination of the capacitor, which is shown over here. I have reproduced this capacitance over here, inductance over here, and this inductance over here. Now, we have two parallel capacitors and find its equivalent, and these two inductors are shown as such. Now, as all three elements are in series, we can change the order of the components. We can combine this with this. As long as they are in series, we can take this to this position, which is it. So adding these two will have the equivalent overall inductance and capacitance. So try various examples and problems in this chapter, and sometimes we need to find DC response of the circuit containing capacitors and inductors. DC response means when current is not changing, when voltage is not changing. Voltage may be zero, current may be zero, may be negative, may be positive, but it is not changing. If the voltage and currents they achieve some fixed values, including zero values. Under DC conditions, a capacitor acts like an open circuit and inductor acts like a short circuit. You know that the capacitor current is CdVc by dt. CdVc by dt. Under DC conditions, there is no change in the voltage across the capacitor. Therefore, the current is zero. If current is zero, the capacitor will behave like an open circuit. Inductor, what is the voltage across the inductor? It is L di by dt. Di by dt, if I is constant, it may be zero, it may be positive, it may be negative, but if it is fixed, so d by dt of a fixed quantity is zero, therefore the voltage will be zero, voltage across the inductor will be zero. If the voltage across the inductor is zero, it means it acts like a short circuit. So here is a circuit, and this is a switch. We will discuss this thing in many circuits in chapter number 7. The switch is initially opened due to the sign. Look at this arrow over here. The switch is opened initially for a long time, such that there is no energy stored in the capacitors and in the inductor, and the voltage and current, everything is zero. This is just in a neutral position, nothing, no voltage, no current, no voltage, no current, no voltage, no current. Because if we open the switch and leave it for a long time, the voltage and current will disappear. So if we close the switch at t equal to 0, t equal to 0 means if we mark the instant of closing the switch as t equal to 0, the switch is closed over here. The switch is closed, then there will be some change in the circuit, in the voltages, in the currents, and if we leave the switch in closed position, means if the circuit remains in this position for a reasonably long time, and you will learn about how much long time it requires to settle into a DC conditions. We'll discuss these things in chapter number 7. So if we keep this switch closed with this excitation, this capacitor will then behave like an open circuit. This capacitor will be open circuit, inductor will be short circuit, inductor will be short circuit. The second end, this inductors will be short circuited, and capacitors will be opened. Now open, no current is flowing, only active circuit is this. This is the active circuit over here. Only this, only this. So in this case, current flowing through 5 volt source and 50 ohm, as no current is flowing, is same as the current flowing through inductor. There is inductor over here, it is short circuited. IL1, IL2 will be same current will be flowing, no current is flowing through. So here, so if it is 5 volt and 50 ohm and 50 ohm, what will be the voltage across this 50 ohm? 2.5 volt and 2.5 volt. Use the voltage division formula. Under DC conditions, switch is closed and T approaches infinity. We keep this for a long time. The current will be flowing through this. Right, immediately after closing the switch, current will be flowing through this. Current will also be flowing through this, but the current flow through this after some time, the current flowing through will become zero as when it is fully charged or it attains DC conditions, and the current flowing through this will finally become zero. Therefore, it behaves like an open circuit. Now we see IL1 is equal to IL2, and it is 5 divided by 50 plus 50. It is 50 milli, and VO is 2.5 volt, as I have said. VC1, what is VC1? This C is in parallel with this. There is some capacitor. It doesn't mean that the capacitor disappears. It means the capacitor behaves like an open circuit. Capacitor is there. Therefore, the voltage across the capacitor, it is in the capacitor is parallel with this. So the voltage, this voltage will be equal to VO. So VC1 will be 5 volt. However, this voltage across this capacitor, there is complete short circuit on this side. This VC2 will be 0 volt. And initial and final conditions means it will be discussed. Initial and final conditions will be discussed in more details in chapter number 7. If the switch has been opened for a long time such that all the energy stored in capacitor and inductor disappears, then as the energy stored across each circuit element is zero, therefore current will be zero, voltage across the capacitor will be zero. So as soon as we close the switch, we find that voltage across the capacitor is zero, current flowing through the inductor is zero, current flowing through the zero, and this will be the initial condition of the circuit at t equal to 0. So if we close the switch, close the switch, and we remain it closed for a reasonably long time, there is energy stored in it, energy stored in it, energy stored in it, energy stored in it. What is the energy stored in it? Half CV square. So there is no energy stored in it. And what is the energy stored in it? Half CV square. 1 by 2 multiplied by value of this capacitance and square of the voltage. Energy will be stored. What is the energy stored in this? Half Li square. So there is some current flowing through, some current flowing through. So energy will be stored, energy will be stored. Now, after when it attains this state, means the DC condition, if we again open the switch from here, then at the time instant when we open the switch, the stored energy will be the initial conditions for the next phase. So we'll discuss this energy storage phenomena in chapter number 7. This is end of part 1 of capacitance and inductance.